Okay, so yesterday we went through the basics of cosmology. I told you how the expanding universe can be described in terms of a scale factor and how to get expressions for the scale factor starting from general relativity, how it depends upon the constituents of the universe, and if you change the constituents, then the behavior of the scale factor can be changed. In the tutorials today, you will try to code up how the scale factor changes as a function of time and depending upon different cosmological parameters. And so you can play around with it. Try to also see the observable consequences of these changes. So if you change the matter density parameter and omega lambda, for example, then how does it affect the observables, which are the luminosity distances or the angular diameter distances as a function of redshift, okay? So please try to code some of these things up and see for yourself how these changes translate into observations. And so the other way around, if you have observations, then you can try to constrain these cosmological parameters. Okay. And so we also yesterday went through some of the things which are required for the distance ladder. So I told you how people have slowly built up distances out in the farther and farther universe, first using geometric methods, then Cepheids to go a little bit further, and then from Cepheids to supernovae to go even further out. And with supernovae, people have been measuring these distances out to redshifts of unity and beyond as well. Okay, so that gives us a measure of the distance, and if you can find the galaxy in which this supernova occurred and measure its redshift, then it gives you observations which can then be used to constrain cosmological parameters. Okay, so that was how people have been trying to get these distances and the redshifts, and so come at the Hubble constant from the late universe side, from observations in the late universe. But there's another way to come at to constrain the Hubble constant, that is using observations in the early universe. Okay, and so one of the things that has made the most significant impact in this subject is the cosmic microwave background. And so you may have heard about this story of Penzias and Wilson. They were electrical engineers. They were trying to establish transatlantic communication channels using the radio frequencies. And they found out that whatever they did, however big antennas they built, there was always some noise which was left over when they tried to transmit signals across the Atlantic. And this signal, they tried, like as any good engineers would do, they tried to figure out what is the cause of this disturbance. And so they tried to look at it in the day and in the night, whether there are any differences. They could not find any. They looked at it in different kinds of directions, whether they could reduce this particular noise, but they found exactly the same noise affecting all their observations. Whatever they did. They even cleaned up their antennas, for example. And so when they established, so if you think about it as some kind of a black body and you establish what the temperature of this black body is, which is giving rise to this noise, they figured out that this temperature was about 3 Kelvin. And at the same time that they made this discovery, there were people in Princeton trying to build an instrument to actually detect this from theoretical side. They had expected that there should be about a few Kelvin kind of a background, which is the relic of the the past from the early universe when things were quite hot. And so these people had discovered already this particular relic. So this is the cosmic microwave background. For this, they received, of course, the Nobel Prize. So after the cosmic microwave background was discovered, then there was a lot of attention being paid to try to see if there are any inhomogeneities in this cosmic microwave background, because you cannot make up the universe that we see just with a uniform background, which is the same in all directions. And so there was a new instrument which was built. It was called the Cosmic Background Explorer, COBE. And what it did is it actually mapped out the entire spectrum of this cosmic microwave background. And you can see that shown here. And this is an observation. So the reason why you don't see any error bars there is just because the errors are even smaller than the thickness of that line. So this is one of the best observed black body spectra. And then so what exactly is this? So in the very early universe, there are protons and electrons. They are trying to combine with each other. But because the universe is hot, as soon as they combine, then there's some photon which will come and hit the electron and give it energy enough such that it does not remain bound with the proton anymore. But as the universe cools down, the photons don't have enough energy. And so then these things can remain bound. And that's the first time that actually these photons can start to free stream in the universe. And then they directly come towards us. Okay, so this is the origin of that cosmic microwave background. This is the reason why people thought that it should exist if the universe was really hot and dense in the early stages. And so, indeed, the spectrum of this also looks like a black body, and that was established by Kobe. But then, in order to discover the inhomogeneities, they had to work quite hard. And so, let me show you how exactly hard they had to work. So, as I told you, the noise that you get from the CMB is basically the same in whatever direction that you see. And so, the temperature of this radiation is also exactly the same in all directions. Okay, so what Kobe did, it was a space-based experiment. It went there, and then it looked at all different directions and tried to figure out what is this temperature, right? So it could measure this temperature in all directions. So that is shown over here in some sort of a projection, which takes all the theta phi's that you see all over in the sky and maps it onto this 2D map. And here, what is shown is the temperature in any of these directions. And you can see that it's quite uniform. It's about 2.728 Kelvin. And this uniform temperature was the puzzling part. Right? So what you have to do is you have to take out the uniform component and then dial the contrast down. Okay? So in order to see any inhomogeneities. So in this case, you take these temperatures, which are there in each and every pixel, and you separate out the mean. So once you separate out the mean and now dial up the contrast, so here you can see the contrast is dialed up to about millikelvin level. So this is about a Kelvin, this is millikelvin level. Only when you dial it down to millikelvin level, then you start to see a dipole emerging. Okay, so there is some direction where the CMB is a little bit hotter, a little bit colder in the opposite direction. And so this coldness and hotness is about a few millikelvin on top of the Kelvin. So 1 in 1,000 already. And so this one was also expected. This is because our own galaxy is not sitting still at that co-moving coordinate grid that we had talked about. It is also moving. And the reason why it is moving is because there are other galaxies and potentials nearby, which causes it to move around. So it's its own peculiar velocity, which causes this dipole. And so if you're moving in a certain direction, then the photons which are coming in the direction that you're moving, they appear a little bit hotter compared to the direction behind you. And so that is this particular effect, the dipole effect. So this can be used to measure the peculiar velocity of our own Milky Way and also its direction. But then since this is another known effect, you can try to remove it out. And once you remove it out, again, you would see nothing unless you dial down the contrast now to tens of microkelvin level. Right? So again, think about the inhomogeneities and the scale of these inhomogeneities. We went from something which was Kelvin level to now tens of microkelvin. That's when you start to see these inhomogeneities. And indeed, this was another thing which was very important. Because this discovery then told us what are the initial conditions for structure to form in our universe. Okay. And it is this particular map then that can be used also to understand what are the cosmological parameters of the universe, including the Hubble constant. So how that works is what I will try to convey to you next. Okay. You can also see this kind of a red splotch here in the plane. So this is the plane of the Milky Way itself. So what happens is there is cosmic microwave background, which is coming from the very early universe. But then it is also getting contaminated, or in the same microwave region that we try to detect these photons, there's also emission from the dust from our own Milky Way. So dust from our own Milky Way contributes to this emission here. And so you need to get rid of this dust in order to see what is the primordial fluctuations that are remaining. The way that this is done is typically by observing at different frequencies. The dust emission from our own galaxy has a particular spectrum that you expect, while the CMB has a different spectrum. And so you can do something called component separation in order to figure out what is beneath this whole noise that you see that is coming just from the galactic plane. Okay, so the dust. So, but after you remove all this, so this is what the COBE collaboration found in 1990. This is the more recent map from Planck collaboration 2015. Is another one in 2018 that was also presented. And you can see how much of a difference these 25 or so years have made. You have gone from seeing structure, which is on larger scale, so the resolution was not that great in COBE, but then when you come to Planck, now there are many pixels which can be seen. So you can think about like low definition TV versus high definition TV. Right? That's the kind of progress that has been made. But already the hot and cold spots. So this is again telling you where the CMB is a little bit hotter and a little bit colder. And so these contrast in the inhomogeneities that you can also see here. So this particular spot here, you can also recognize it here. All the structure that you see is already present also in COBE, right? So this is just at a higher resolution. That's all. So what is the physics that governs the cosmic microwave background? So what is happening is there are initial inhomogeneities in the density field. And so there's a little bit more of matter in certain regions, little bit more of photons in certain regions. And this sets up pressure density waves. And the reason why this is happening is initially gravity is trying to get all of this material clumped. But as soon as it clumps a lot, then the photons, which are also coupled with the baryons, they start to exert radiation pressure. And so because of this, it cannot keep on condensing. And then because of the radiation pressure, it starts to bounce back. Okay, and so this sets up pressure density waves or sound waves in the early universe. And it is these sound waves which you can actually see in the inhomogeneity maps. So it can be mimicked by something which looks like this. So there is gravity which is pulling down the baryons. And then there's the pressure which is because of the photons which are coupled to these baryons, which then try to bring them out again. And these potential wells that are created, those are created by the dark matter in the universe itself, which is not interacting at all with the photons. Okay, and so it is in these gravitational potential wells that you start to see these sound waves going off, and then the physics of these sound waves is what you can use in order to learn about how to take the observations and then turn it into cosmological parameters. So the density fluctuation field that is present in the early universe, you can decompose it into Fourier modes. And so each of these Fourier modes will have a certain wavelength. And in these different wavelength Fourier modes, you will start to set up these sound waves, right? And so you will have some potential wells and hills and wells, and you are setting up these sound waves. But then there are also different Fourier modes, right? So this is, I'm just showing you one particular mode. There will be Fourier modes with different wavelengths. And so all of this total will combine to give you the final density field that you actually see. So whenever there's compression happening, it's heating up. And whenever there's a rarefaction, then it's actually cooling down. And so this sets up also waves in the temperature field itself of the photons or of the radiation field. Okay, so then there will be, as I said, there will be some waves which will be like higher frequency, low frequency waves. So all of these together will give rise to the temperature power spectrum that you see. So let's look at some of these waves, right, and how they actually, how their amplitudes change. Right? So what you are seeing here is time on this axis, x-axis, and the delta t by t on the y-axis. So you start with something which has, say, a low temperature compared to the mean. And then what will happen is, as time goes on, it will fluctuate, right? So instead of having a low temperature, now it will have a high temperature, right? So as time goes on, you will see that these, yeah, so that this delta t by t at a particular position, it will start to increase and reach at a certain position. Okay. So what is happening is that these these initial fluctuations are set up really early on in the universe. And then as time goes on, these fluctuations are changing in their amplitude. But at a certain point of time, what happens is the universe cools enough that the photons and the baryons, they don't remain coupled anymore. And if they are not coupled anymore, then you basically, the photons after that point, they just start to stream away towards you, right? So they maintain this temperature, right, at the point of recombination, right? So recombination is this process when the the protons and electrons combine and photons are not energetic enough to dislodge them. So these photons which are left at this particular point, they are the ones that reach you. Right? Now, you can consider different modes, right? So this is one particular mode which just reached its peak, but there could be other modes which reach their peak and then come and then reach another trough again. Okay? There could be some other modes which don't even reach this peak, so they are somewhere in here. Right? And so, depending upon the time that is present between the time that fluctuations were initialized compared to when recombination happened, the different wavelength modes they will be caught in a different phase, right? And so some will be at the peaks of their amplitude, some will be at their nulls, and some will be somewhere in between. And so that's why different Fourier modes, they give you a different variation in these temperature fluctuations. Okay. So this is about 380,000 years. So it gets set up at in the very early universe after about inflation, and then these things are basically proceeding. Right? And
by the time of recombination, only say about one cycle has happened.
No, so how many cycles have happened will depend upon the wave number, right? Because different fluctuation modes, they will fluctuate with a different time scale. Okay. And so there will be only certain modes which will undergo like half a cycle, for example, here. And then there will be some which will undergo one full cycle. But that depends upon the wave number. Okay. So again, you have this initial density field, you decompose it into Fourier modes. So now you have different Fourier modes, and each of these Fourier modes will have a different time scale. Okay. And what is then the time scale? Time scale defined by, so for time scale, you need something which has a velocity and something which has a length scale, right? And so the velocity in this case will be the sound speed, okay, because how quickly can sound travel? And so that is CS, so the sound speed. And then the length scale comes from the inverse of the wave number, or the wavelength here, right? And so you can combine this sound speed and the wavelength to get a time scale. And only those wavelengths which have time scales which are related such that they get caught in their peaks, they are the ones where the fluctuations will be enhanced. Okay. Yeah, so this is related to the fluctuations amplitude and what is the gravitational potential fluctuation at a particular point. Okay. And so these will be different. And so each of these wavelength modes will have different fluctuations. And so the amplitudes themselves, we have to measure and find out. But even whatever that amplitude is, we know that the fluctuations which are caught in this particular, or which are present in this particular mode, they should be amplified.
These initial conditions are set by the primordial power.
Yes, yes, indeed. Yeah.
After
Yes.
during
No, after the end of inflation, it's inflation which sets up these initial conditions. And then there is a period during radiation domination, and then the period during matter domination, where all of these fluctuations are basically going on. Velocity of sound and K inverse. That's basically what sets the time scale. No, so that will come because any time scale will also have an H inverse involved in it. Right? Yeah. Okay, so then, so let's look at how you actually see these fluctuations in the first place. So let's assume that this is some kind of a wavelength mode in which you are situated. And let's suppose you are located somewhere here. Okay. So initially what will happen is, let's suppose you are sitting in one of these red spots somewhere here. And then initially, as soon as the CMB has been released, what you will see is just a hotspot, right? Because you are only seeing photons from your own neighborhood. Okay. But as time goes on, photons from a little bit further away will also start to hit you. Okay. And that's when you start to see all this structure that you see here. Okay. So initially, there will be all these oscillations that are going on, right? And at some point of time, these oscillations will stop. And after they stop, then you start to receive photons, okay, coming towards you. So this is how these photons reach. So initially, only the nearby regions, they reach you. But after some point, the regions which are further outside, they start to reach you.
Okay. Does that mean that the CMB spectrum that I observe today will be different from the spectrum I observed 10 years hence?
Yes.
Not the black body temperature, but the
yes. The fluctuation spectrum is expected to change over time. Yes, as photons from even further out, they reach you.
But you showed Kobe and Planck.
Yeah, so that means that the time scales that have passed between 25 years is not enough to see this change, right? Because even within 25 years, the fluctuations on very smaller scales would have changed. Right? You can calculate what this time scale change would be, right? Okay. And so what you in the end observe, right, is like a circle, and this spatial inhomogeneity which was there in the temperature field now appears to you as an angular inhomogeneity. So inhomogeneity in one direction compared to the other, and so on. So that's what is the cause of these fluctuations that you see in the CMB. Okay, so let's recap the photons and baryons. They are coupled as a fluid. And the speed of sound in such a medium is the sound speed itself. You can show by doing dp by d rho. It's related to the speed of light divided by square root of 3. And so the sound horizon that you can calculate, so the distance that sound can travel between the time when these sound waves were initiated and today will be the sound speed times the time to recombination. And so wave numbers, which are related to this particular length scale, they are the ones that will have enhanced fluctuations. Okay, so you can see certain enhanced fluctuations already here. Like there are scales on which these fluctuations are quite large. Okay? And so there is a statistical way of actually doing this, of calculating what these enhancements looks like. And these things is called the power spectrum typically. So what you are seeing here is the RMS of temperature fluctuations when the CMB map is smooth on particular scales. Okay. And what you are seeing here is the angular wave number L. And so here is large scales, here is small scales. You can consider this L as roughly 1 over theta. So you take the CMB map, you smooth it out on, say, the largest scales, and you calculate its variance. Okay. You understand what the variance is, right? So you take the CMB map, you smooth on large scales, and then you ask, what is the temperature here? What is the temperature here? What is the temperature here? And so on and so forth. And then you make a histogram of it and find the variance of this Gaussian. It actually looks like a Gaussian, and then you can measure the variance. Now you go to even smaller scales, and then again repeat the same exercise. And so at different scales, you will start to see different RMS variations in the fluctuations. And that is what is being plotted here, okay, as a function of scale. And so what you see is that there are certain scales where these fluctuations peak, and then there are other scales and so on where you also see these other peaks. Okay. We'll come to what is varying here. Okay. But once you see these peaks, what you are seeing basically is the sound horizon that was present at recombination. Okay? And if you look at also these peaks, you can see that this peak and this peak and this peak and this peak, there will be integral multiples of each other. And these integral multiples are basically related to the fact that the mode which reaches the peak at the time of recombination, you are seeing its overtones. Right? So if you're blowing through a pipe, those of you who play music, they will know when you hit a string or you blow through a pipe, you don't just excite the fundamental node, you also excite the other modes and the other overtones. And these are the overtones that you are also seeing. Okay, so just like the main mode is caught at its maximum of its fluctuation, there are modes which have like twice the wavelength and so on. They, half the wavelength. They will also be caught at their maxima. Okay. And no, so I'll come to this. Right. Yeah. Yeah. Okay. So once you know that the time to recombination will give you a length scale, then now you're set, right? Because if you have a length scale and if you have a measurement that you can do from today, then an angle and you can measure the angle of this length scale. And so that gives you the angular diameter distance. So once you have the angular diameter distance, then you can ask, what does it tell me about the cosmology itself, right? Because you have angular diameter distance at a particular redshift. And so just like I told you that if you have distance observables as a function of redshift, you can constrain cosmological parameters. So because you have an angular distance measurement here, you can again constrain cosmological parameters. Okay? And so that's what is shown here. So one of the main things that you can constrain is this omega k, which is the curvature, the energy density in curvature. So how is it defined? So this is basically omega k is 1 minus omega matter minus omega lambda minus omega radiation. And each of these numbers is basically rho matter divided by the critical density of the universe. And this one will be rho lambda divided by the critical density and rho radiation divided by critical density and so on and so forth, right? So you take all the components of the universe, whatever is left out is what the curvature of the universe is, this omega k parameter. So you change omega k, what happens is that you change the angle at which you would see that particular enhancement in fluctuations, okay? Just because you are changing the angular diameter distances, and so the location of this enhancement changes. And that's why you can actually constrain this omega k pretty well if you can measure this power spectrum. Okay. And I will also quickly show you how good these measurements are right now. Okay. So here, this 1 minus omega mc, omega r is quite small, and so on. And so that's the reason why this is, I think omega lambda is fixed here, and then only 1 minus omega m is varied. Okay. So that means that the curvature is varied, and that's the reason why you see it shifting. So in addition to that, you can also look at the odd and the even number of peaks. So if you look at this peak, the first peak and the second peak, then the ratio between the heights of this peak also tell you about the amount of baryon density that is there in the universe. So there's dark matter in the universe, baryon density as well in the universe. So if you change this baryon density parameter, keeping the dark matter density fixed, then you start to see that there is a difference between the height of the first peak and the second peak. Okay? And even all these other peaks, basically. And so you start to see that you can, like if you measure these power spectrum really well, then you can actually start to constrain different cosmological parameters. Similar is true, you're changing the omega matter here, and then now you can again see that there is a difference. Now the first and second peak, roughly the ratios are same, but omega matter, the first and third peak, that ratio is changing as you change omega matter. And so if you can map out each of these peaks really well, then you can constrain the cosmological parameters independently just by looking at the temperature fluctuations data. No, baryonic matter is matter that for which the standard model of particle physics applies. Total matter is baryonic matter plus dark matter. And so in this case, it will be total matter. Yeah, because it's general relativity, all of matter drives what is happening to the scale factor. Right? Sorry, I have not gone through all of these derivations yesterday, but you can find it in my lecture notes as to how exactly this comes about. How is this omega k related to the small k in the equations, in the Friedman equations, for example. Yeah? So those are in the lecture notes. Just take a look at it when you get time. Okay. So similarly, there is this damping that happens on on very small scales. And this is also related to the omega b h square parameter. So you can see that there are many bells and whistles that are there, and you can use these measurements in order to constrain the cosmological parameters. Okay? So the location of the first peak, that tells you something about the geometry of the universe, and then the relative heights of these peaks that can tell you about the dark matter and the baryon densities. And so you can learn about the geometry of the universe, the constituents of the universe, all of this from just these observations of the CMB. Why there are? Yeah. Why both of them are same? So this is basically, this is not an observational result right now. So the observations are somewhere here. Oh, sorry, this is also an observational, maybe from early on. So the cosmological parameters are basically such that they give you this kind of ratio, right? And so now you have to find out by looking at these observations what the cosmological parameters mean. And that's exactly what was done. So this is the Planck version of it. Okay, and you can see the measurements are here. And just like it was harder for you to see the error bars on the temperature pulse, the temperature, the black body spectrum from CMB. Now this is the temperature fluctuation power spectrum, right? And it's again very hard to see some of these error bars because it's so well measured. It becomes harder to measure things on large scales just because we have only one universe. So you're dominated by something called cosmic variance, just that we have one realization of the universe to probe. But other than that, you can see how well things are measured. So even if I didn't give you the red curve, you can easily identify many of the peaks that you see here. Right? Initially, that was not the case when things were first discovered. It was quite noisy, but now you can see how well it has been measured. Right? And yeah.
In all these diagrams, as we go to larger L, that is smaller lengths.
Yeah.
So the amplitude is invariably smaller. So was that information put it in the primordial power spectrum itself?
No, partly, the P of k itself goes as k to the n as set by inflation. So on small scales, the P of k will be large, right? But there are many processes in the early universe which actually prevent the growth of fluctuations on small scales. And some of this is also processes, it's a process called silk damping. And so that is what gives rise to this kind of damping that you're seeing. So exactly how the matter power spectrum changes with time, again, it is present in my lecture notes. So there's something called the Mazoros effect, which creates a turnover in the power spectrum. And the peak that you see, for example, of the power spectrum, of the matter power spectrum, it is related to the horizon at matter radiation equality. Okay, so that is where the peak of the power spectrum comes. And so all these things again are explained in more detail in the lecture notes. So again, I didn't want to go into too much of these details here. Yeah. Okay. So these are the results that Planck got for the constituents of the universe. So as seen today, there's dark matter about 26.8% of it, dark energy 68.3%, and ordinary things that we know mostly in terms of hydrogen gas in the universe, that's about 5%. Okay. And this basically constitutes the entirety of what we see today. There's of course trace amounts of radiation. That's why we see the CMB and make all these observations. But when you put it in terms of the critical density of the universe, it's nowhere close. You cannot even see it. But that was not the case when the CMB itself was released. And at that point of time, if you take Planck's results, then this is what they predict. The dark matter at that time would constitute 63%, atoms about 12%, and then photons plus neutrinos about 25%. Okay, at the time that the CMB was released. And you can see here, to here, what has happened is dark energy has grown up. And the reason is that the energy density in dark energy, it remains constant. Any ordinary matter, it falls down as the universe expands. Okay? And so even though there was not much of dark energy seen in the early ages, now it is starting to dominate. But if you look at the ratio between dark matter and ordinary atoms here, and dark matter and ordinary atoms here, it should be the same, because these things are just going down as 1 over volume, as the volume has increased from the time that CMB was released to today. So with all of this, what does it mean? Yes, sorry. Where does dark energy feature in the earlier? You mean, okay, so in the power spectrum measurements here? No? Yeah. Yeah, so dark energy has an effect by changing the angular diameter distances. So if you have dark energy, causes an accelerated expansion of the universe. And so in effect, it affects the geometry of the universe, right? I mean, its effects can be seen from the geometry of the universe. Okay, so there is a particular plot that you can try to see in the matter omega lambda plane. Okay, and so if you let both of these parameters free, okay, this is the line corresponding to a flat universe. I don't know if I put that plot in or not. And then the CMB basically puts you somewhere close to here. Okay, it's not exactly, it does not tell you exactly the curvature. There's some more information about dark energy coming on from these lowest L values, from something called the integrated Sachs-Wolf effect, where dark energy causes the decay of potentials. Okay, and so what happens is the CMB photons, they are traveling towards you. When they are traveling, they encounter a potential well, they fall into it, and by the time that they are coming out, the potential well also decays. And because the potential well decays, now the energy that was gained by falling in, now they don't have to lose as much energy. And so on some of these larger scales, you start to see the effect also because of the decaying of this potential. So that also starts to give you some constraints. So that can be seen here, for example. You change omega k or this omega lambda, you can see things here, how this thing is starting to go up. Okay? So that allows to then constrain all these different parameters. Okay. So in the end, what is done is you take these observations, you run it through the model, and you predict what these fluctuation power spectrum should be, and then constrain the parameters based on the observations that you have, given the error bars with which you have measured these quantities. Right. Relativistic at earlier, yeah. No, so they even start to put in the masses of the neutrinos when carrying out some of these analyses. Yeah.
If it's not masses, that how the distance between photon were detected? Like
Right. So this will assume a certain delta m depending upon one of the hierarchies given the delta m square measurements. Okay, so what does it mean for the Hubble constant then? So you take all these observations and you can calculate them or ask from the CMB temperature power spectrum itself what the Hubble constant is, and that lies somewhere here. Okay, and this is for the flat lambda CDM universe. Okay, so there is no assumption of curvature here. If you free up curvature, then there are other problems that happen. In fact, this Hubble constant shifts even further to the left. Okay. And these are the measurements that are coming from the low redshift universe. So the kind of measurements of the Cepheus, the geometric distance measurements, plus the supernovae all combined together. So this is the posterior distribution that you see on H naught. And this is what comes out from Planck. And you can start to see that they are not exactly matching. And so what is exactly causing this discrepancy is not fully understood. Okay. So this is in the flat lambda CDM model. People have tried to come up with different ways of modifying the standard lambda CDM in order to see whether this discrepancy changes or not. So for example, people have thought about early dark energy models, which can also try to relieve some of these tensions. It's very hard to do. So if you try to fix this, then something else breaks. Okay, so that's the reason why this is such an important tension. It's very hard to understand what is going on. But as you know, there are all sorts of systematics as well. I mean, when you looked at standard candles, even if one of these rungs of these ladders, of the distance ladder that we talked about, if there is some problem there, then of course it will translate into a measurement of a problem in the measurement of the Hubble constant. And if that's the case, then again, you can start to see these discrepancies. So what exactly is going on I mean, this is one of the biggest puzzles that remains now. Okay. So that's where gravitational waves come in. Okay, so finally we are at gravitational waves. And so this particular discovery of gravitational waves was very influential, of course. In 2015, this was discovered by the LIGO-Virgo collaboration. So you can see these two detectors, the one in Hanford and the one in Livingston. They sent out this kind of a data. So this is done using interferometric measurements. And so what you're seeing is the strain on the y-axis and the time on the x-axis. And you start to see this kind of a very distinct feature in the strain as a function of time. And so this particular discovery, it is coming, or these gravitational waves are being emitted because of binary black holes which were orbiting each other. And as they orbit each other, they emit gravitational waves, and then they lose their orbital energy, come closer and closer to each other. Then that causes the frequency to also increase, and so on and so forth. So you can see all these features basically here. So the frequency of these strain waves that you see, as a function of time, it is also increasing. So it means that the waves are getting both higher amplitude as well as higher frequency. And then at some point they merge, and then you start to see something called a ring down of this black hole. So we'll try to understand where these gravitational waves are coming from. I will not try to go through the GR derivation of any of it, but I'll try to give you a more intuitive understanding of what's going on, why this particular kind of feature that we see, and what are the parameters of these gravitational waves that you can actually constrain. Okay, so we'll do some sort of a semi-classical way of doing this. And then hopefully that will give you some insight into what is happening. Yeah.
That to say that the CMB analysis of gravity is much precisely calibrated than the CFD, because the distance ladder is at each point you are assuming that you have type A one,
Yeah.
1 over.
Yeah.
So I'm just asking that, like, is it?
Yeah, I mean, people definitely there is a lot more trust in the CMB results because it's early universe physics. It's something that we very well understand. But there could be problems, right? And so, see, CMB is the observations which are done at in the very early universe. Then to come to today, to predict the expansion history of the universe, you have to assume a model, right? If something breaks in the model, then of course your measurements may be off. So there is a possibility that the cosmological model itself is wrong, right? So that does not mean the analysis that was done by Planck is wrong. It's just that the model that they use to interpret those observations is wrong. And then that can give you a different answer for the expansion history. That's the reason why these measurements are so important, right? You want to do the local measurements really, really well and really precisely in order to see whether the cosmological model itself is breaking or is it just some systematics that we are stuck with.
So when is that early dark energy sequencing? Is it between recombination and today or even before recombination?
No. I think it is, I don't think it is before recombination. I think it is between us, but it is invoked early enough that it does not look like the constant dark energy that we see today. Yeah, so those papers I can refer you again to what exactly they are doing. Okay, so let's see if this simulation runs. So this is a simulation of GW150914. You can start to see these two different black holes going around each other and emitting these gravitational waves. And as they come closer and closer to each other, you can see this frequency also rising. And then at a certain point of time, they will merge and then emit a last burst of these gravitational waves and then settle down. So it is this kind of physics that we will try to just quickly get some dimensional feeling for what exactly what are exactly the parameters that are important when we look at gravitational wave events. Okay, so let's consider, I mean, you have seen there are two black holes. Let's suppose they have masses capital M and small m, okay? And then you're trying to think that they are going on circular orbits. And so let's try to calculate the frequency with which they will be going around each other. Can you try to do that quickly? Okay, how should we proceed? Maybe some of you can help me. So just a simple Newtonian problem, right? This you should have done before, so maybe a white chalk. There's a capital M and then a small m. The center of mass will be somewhere here. And this is a distance capital R, and this is a distance small r. So how will you establish? This is going around in circular orbits. So what will you write down? The reduced mass, but before we get to the reduced mass, let's just try to write down the equation of motion, right, for any of these masses. So let's just consider this big mass, then m omega square times r. This should be equal to gmm by r plus r the whole square. Is that okay? Right? But then these capital R and small r, they are related, right, to each other because this is the center of mass. So m times small r should also be capital M times big R, right? And so similarly, if I do is this okay? Yeah. So what I've done is I have added capital M times small r on both sides. Okay. So this allows me to get rid of basically the small r in favor of these quantities. Or in fact, the other way around also for capital R. So this will be m times r plus r divided by m plus n. So the capital R I can substitute. This m anyway goes. The capital R comes in the denominator here. So that is m times capital R plus R divided by m plus n. Yeah. So this thing cancels out. And you get g times m plus m divided by r plus r the whole cube. That's what is written there, I hope, right, for omega square. So the frequency of these two objects going around each other, that depends upon their masses, but the separation with 1 over r cube. This is also some form of Kepler's third law, right? T square is proportional to a cube. And omega square will be will be proportional to 1 over t square, right? And so you get this. Then you can also write the sum of the kinetic plus potential energy. So what will be this sum? It will be minus half GMM. So the total energy, let's write it down, minus half GMM, virial theorem, right? And so this thing, now what I can do is, I can try to get rid of this capital R plus small r and try to establish the total energy in terms of the frequency itself, frequency of the orbit itself, right? And so in this formula, GMM divided by R plus R, now I'm going to substitute. So what is the R plus R? That will be G times M plus M divided by omega square, the whole raised to 1/3, right? And so you substitute that, you get a formula that looks like this. The E dot is proportional to omega to the 2/3. Now you see all the separation dependence has completely gone. So I've established what is the energy in terms of omega itself, right? Now in GR, what happens is that the gravitational wave radiation or the gravitational wave field that is generated, that is related to the dipole. That is related to the quadrupole of this mass distribution, okay? And the quadrupole in this case comes out to be the moment of inertia. And if you take the power, then it will be the gravitational field square. And so the power radiated is proportional to the moment of inertia squared, okay, of these gravitational waves. And so the radiated power that is there in gravitational waves, it should be related to I square. But in addition to I square, it is the energy itself that it can be related. So it can be related to the frequency here, omega. And the other gravitational, other constants, physical constants that remain are the gravitational constant and the speed of light, right? And so it can only depend upon these quantities. So G, C, I square, and then omega to some power. So what you can do is you can just carry out a simple dimensional analysis, okay? So maybe let's do that quickly here. So if you look at the radiated power, so let me erase this out. Okay, so the radiated power, if you assume that it's I square, and then it is related to C to the alpha, then omega to the beta, yeah, and then G to the gamma. And then you can try to figure out what these alpha, beta, gammas are. Okay. So do you want to quickly do this? So it's some constant K times this. And remember this moment of inertia. So this is something like mr square, right? C will be, or m length square, right? The whole square. C is length time inverse raised to alpha. Omega is T inverse raised to beta. And then what is G? G you can write as V square R by M, right? So it's L square t to the minus 2, then L, right? So V square R, and then divided by M, right? The gamma. And then this is power radiated. So this is energy per unit time. And so again, you can write down the expression for that. Okay, and then start to do the dimensional analysis. And once you do it, you will see that it comes out to be these powers. Okay, so omega to the 6th and c to the 5th. Okay, c to the 5th in the denominator, omega to the 6th in the numerator. So the radiated power that you see is related to the frequency of these gravitational waves. Yeah, so this is coming from GR. So that's the reason why we fixed it. So that we don't have to then derive this, right? So the gravitational field that is generated is proportional to the moment of inertia. And so the energy radiated is related to I square. Okay, so once you do that, then you should be able to get basically this expression here. Okay. So what does this mean, right? So you can see that the energy was related to omega to the 2/3, but then there is now some power which is being radiated, so energy which is being dissipated. And so now a change should happen in omega. And so what you can do now is take the definition of the moment of inertia, okay, put that in here, and then equate it to the derivative of this total energy. Okay, and that will tell you how the orbit of these two black holes is going to shrink as time goes on. This is purely Newtonian right now. So of course, this will not work, and you have to come up with better waveforms and so on. But this gives you an intuitive picture about what are the main dependencies. Okay. So if you do this, you take this power that you calculated and you put in the expressions for I into this power and then equate it to dE by dt here. Okay. So if you do dE by dt, then the thing that is changing here is omega, and so you get it in terms of omega, d omega by dt. Yeah. And so you get how the energy is changing. Okay. And so the equation that you get in the end looks something like this. Okay. That there is a relation between these masses and the d omega by dt. Okay. And it's some complicated combination. Maybe it is worth quickly doing this, I don't know. Or maybe in the tutorials you should do it, okay? Try to go from some of these equations back to try to see that whether you can derive this equation. This thing, it's called a chirp mass, okay? So this mass, I mean, it's all these, so if you, okay, maybe we should just quickly derive it rather than me telling you where this is coming from, right? Okay, so the radiation is this, I square omega to the 6th, c to the 5th, okay? And this we are equating basically to this quantity, dE by dt, right? So dE by dt is okay here, right? So 2 by 3 comes down, it cancels with this half, so you get a 1 by 3. G to the 2/3 remains as it is, the mass terms remain as it is. This becomes omega to the minus 1/3 d omega by dt. This is okay, right? So we can start from this expression. So 1/3 G to the 2/3 mm by m plus m to the 1/3 omega to the minus 1/3 and d omega by dt. Right? But our moment of inertia, so what is the moment of inertia? This is, oh, I should not write here. Okay. Let's see. Right. So the moment of inertia is basically mr square plus capital M r square. And then you can again substitute so that this r and this r in terms of these quantities. so that you can get that moment of inertia to be that quantity that you see there. Okay? So you see you have a alpha and then an I square. So mm by m plus m, the whole square, and then r plus r to the fourth, okay, omega to the sixth, and c to the fifth. And this one is 1/3, again, the same. Right? So this is equal to this. And now you basically start collecting all these terms, okay? Sorry, there is an omega square, sorry, omega, okay. Omega to the sixth is there, blah, blah, blah. I'm sorry? G? Gravitational constant is missing. No, this one, yes, sorry, there's a G here, right? Absolutely. Thank you. And this R plus R, then you can again try to remove the R plus R by going to the omega equation. Okay. So you can see that the R plus R will be omega to the minus 2/3, right? So this R plus R, this again you can try to get rid of. And so it is omega to the minus 2/3 raised to 4. So omega to the minus 8/3. Okay, so all these powers are then combining in order to finally give you that expression for d omega by dt. Okay, and maybe I know I don't know. Maybe we should just derive it, right? So 1/3, 2/3 mm. Okay, and then the r plus r to the fourth power. This again, I have to substitute from there. So r plus r to the fourth power. Let's first write r plus r. Oh no. R plus r will be g m plus m divided by omega square to the 1/3, and so this to the 4/3. Yeah? You should do this, okay, in your notebook at some point. Doing it on the board is always tricky like this. So now you can see here, so this is m plus m the whole square, and then m plus m to the 1/3. This is mm square, and then this is mm, right? So these things basically we need to collect all together. So let's try to do that. So there's a squared here, and then a 1 here. So that means I will get an m times m. Okay. Then for m plus m, you can see that there is a squared, so minus 2. So 4/3 minus 2 on this side. And what is there on this side? Minus 1/3. Right? So what will you get? So 4/3 minus 1/2 plus 1/3, right? Okay, and so what is this? 4/3 plus 1/3 is 5/3. So 5/3 minus 1/3, right? And so is that right? Just correct me if I'm wrong, okay? You get alpha g. No, g again we have to check. So 1 plus 4/3, 1 plus 4/3 minus 2/3, right? 1 plus 2/3. So what is that? 5/3, right? Okay, we are getting somewhere. And then omegas, maybe we can start to put on the other side. So what are omegas? Omega is, we will put it here. So omega to the minus 1. So this is minus 1/3. And then here it will be what? Omega to the minus 8/3. So plus 8/3, right? Correct me, okay, if I'm wrong. And then minus 6. What does this give? Minus 11/3. Very good. Okay, anything else? C. C remains as c to the fifths, right? So yeah, whichever direction, I don't know. Okay. So let's see if that roughly matches or if I made some mess somewhere. Okay, so c to the, I think this should be okay. It's just that I have to raise all of this to 3/5 power. Okay, so if I raise this to 3/5, let's forget about this alpha for the moment. I get G exactly like this. I raise to 3/5. And here also I raise to 3/5. Okay. Yeah. So that gives me a C cube, right? C to the 5 raised to 3/5 is C cube. The G is in the denominator, which is okay, good. There's some 1/3 alpha. So this 3 and alpha, they are gone here. Yeah, so it's looking okay, right? Yeah, not bad. So what you can see is, if you can measure this d omega by dt, right, how the frequency is changing as a function of time, you can learn something about this particular mass combination, okay, directly. Okay, and just check that the dimensions are correct. This is actually a mass, right? So this is m times m to the 3/5. So this is mass to the 6/5. And then there is a mass to the 1/5 in the denominator. So indeed, it has a dimensions of mass. Right? But it's this weird combination that is there. No. I mean, even after you do all of this, I mean, finally, you have to reach here. The reason why I did it in that manner is just to simplify things. Yeah, but if you work out all the equations, finally, this is what you will get. Yeah. So gravitational waves, the d omega by dt, this thing where you start to see a sudden increase in the frequency, that thing is now called a chirp, because you start to see that the frequency is like increasing as time goes on. And so that's why it's called a chirp. And this chirp is what you can directly see, right? Even from the waveform, you can easily see. And so how quickly this frequency is changing, it is related to this chirp mass. Yes. Yes, exactly. Right. That's the reason why chirp mass is well. Okay. Okay. So now the thing that happens is the frequency of gravitational waves that you see is actually such that two times the orbital frequency is actually the gravitational wave frequency. And so that's, you can substitute this to figure out how the gravitational wave frequency that you observe is related to the chirp mass. Okay, so this is a small thing that you also need to do. Whether the masses are like this or like this, you get the same gravitational waves coming towards you. And that's the reason the frequency is twice. Okay, and so the observed signal then can give you the chirp mass. Okay. So again, just backing up, what you observe in the interferometers is the change in these lengths that are happening in the arms of the interferometer. And this change in the lengths are what are shown here, basically this strain value, delta L by L, as a function of time. And you can see these kind of sinusoidal looking features. They have, at a particular time, they have a certain frequency. And so you can measure by averaging over a small amount of time period, what is the frequency of the gravitational waves that are reaching you. And you can see how this frequency is changing as a function of time. And that's what is shown here. Okay. Everybody with me here until here?
So yeah. Is the chirp mass a time dependent quantity? Because on the right hand side, omega and d omega by dt, which are functions of time, right?
Yes, so you can calculate what happens to this d omega by dt. I mean, if the d omega by dt stays constant, then what this functional form is going to change like, right? So even this omega to the minus 11 by 3 times d omega by dt in the Newtonian approach will remain constant throughout this process. Okay, but in reality, of course, you have to solve all the GR, numerical relativity, and whatnot. So all this thing will not remain exactly true as you come closer and closer, of course. But even in numerical relativity, the functional form is well determined by this chirp mass. Okay, that's the reason why this is also the most well measured quantity. And that's the reason why I wanted to show you this derivation, just to give you a feel for where it comes from.
So
yes.
Yeah. So get some idea about before module can get.
Yes.
But is there any clue about like, so in spiral dynamics and before module that is clear, but after that what happens?
Yeah, so after that, basically, once the black hole merges, then there are these inhomogeneities which are there in the black hole, right? As soon as you merge, and then these things are just radiated away until the black hole just settles down to its final stage. Yeah. To then, yes, of course, no. No, I think usually, and maybe Ajith can correct me if I'm wrong, what people do is they take the earlier stages from all these kind of higher order corrections, and then later on you have to run numerical relativity simulations to see what the waveform will look like. And then post the merger, what the ring down is, where the black hole is actually removing all the inhomogeneities that are present, that is again, that can be worked out analytically. That's correct, right? Yeah. But I'm not an expert on this. He will be the expert on these things. Okay. Okay, so let's look at the chirp mass then equation. So this equation that you get, this chirp mass is related to this quantity. You will notice that if you are in a, if you are in a cosmologically expanding universe and this gravitational wave emission is emitted like very far away at higher redshift, right? Then the frequency that you will observe will not be the same as the frequency that was emitted, right, at that location. And so even when the calculations are done, they are done for a faraway observer, but faraway observer in a static universe, not in an expanding universe. So if you take into account the expansion of the universe, then you know that the frequencies should go down like this, right? So the detected frequency will be the actual frequency divided by 1 plus z, okay, if the redshift is far away. So this is again related to the fact that the wavelengths, they increase as time goes on. And so the frequencies, this is what you will see. The frequencies should decrease, right? So we have seen binary mergers out to a redshift of even 1. Okay, so it's quite far. GW15, 1 and 14 was still closer. Okay, but so we are coming there. That's exactly where we are coming now. Slowly. Yeah. So you see that there's this omega divided by 1 plus z. That is what will be seen at the detector frame. But we also know that any time that is present in the frame of the merger itself, that time should be related to our time with again another factor of 1 plus z, right? So whatever happens at that time multiplied by 1 plus z is what you will see. Okay. And so this time frame in the detectors, this time is also dilated, you get t times 1 plus z. Okay. So these two things are related. So then what happens if you now substitute this thing, omega d is omega by 1 plus z, and this td is t times 1 plus z. You will start to see that you will obey exactly the same equation if you say that the detector frame mass is equal to this actual chirp mass times 1 plus z. Okay, so you try to substitute these things, you will see again an equality. What this means is when we measure the actual frequency change, d omega by dt, that will be related to the d omega by dt that is there in the frame in a non-expanding universe, right? And so that is different from, these two things are different. And by measuring whatever we see today, we can actually measure only the detector frame mass. Okay, so we measure a degenerate combination of the true chirp mass and the redshift of the event. You never measure each of them separately. You measure this combination, m times 1 plus c. Okay, so this still does not tell you how to get the redshift of the event, right? So the one thing that we have not used so far is the fact that there is also an amplitude to the gravitational waves. Okay, so thus far we have only used the shape of the signal, not the amplitude. Okay, and for the amplitude, again, what you have to do is you have to look at these waveforms that you get, and what are the amplitudes of these waveforms dependent upon. Okay? And so this is now higher order expansion. So we are not using just Newtonian gravity in here. So once you do that, then you get basically these gravitational waves have two different polarization. One is a plus polarization and one is a cross polarization. And what you see is that in the frequency domain, you can write down these two polarizations like this. So this thing is some kind of an amplitude which is dependent on the chirp mass and the frequency. There is a dependence on the inclination angle. So the orbit of these binary black holes, the angular momentum of this orbit will form an angle with respect to the line of sight towards the center of mass. Right? That angle is called the inclination angle. So that iota is here. So the plus polarization, it depends upon this kind of a combination, and the cross one depends like this. Okay. There is a phase term which also evolves as a function of the frequency itself, so you can see what this looks like. Okay. But you look at this amplitude, and this amplitude has a dependence upon the distance. Okay. And this distance is basically the luminosity distance. So it's a gravitational wave which is traveling towards us in the universe, and so its amplitude is going to fall down as the distance. And so this luminosity distance is what comes in. Okay. So by measuring the amplitude and the shape of these gravitational wave events, you can get the chirp mass times 1 plus z and the distance to this event. If you had a cosmological model, then you can break all these degeneracies. You can get the actual chirp mass. So whenever people say that, okay, we have observed black holes with 30 solar masses merging with each other, then they would have assumed a particular cosmological model. They would have taken this amplitude measurement, gotten the distance out of it by using also the chirp mass, by looking at the behavior, right? And then they would have told you what the actual chirp mass is. So they would have gotten the detector frame mass first, used the distance to get the redshift, and then from there converted the detector frame mass to the actual chirp mass. You don't. In principle, you don't. If you know the cosmological model perfectly, you don't need, right? But that is where, sorry. Exactly. That's right. So that is exactly where we are going to go tomorrow and day after tomorrow and further, is that you take these gravitational wave events, you measure the shapes, it tells you something about the detector frame chirp mass, right, to first order. And then you measure the amplitude of this gravitational wave. It tells you something about the distance at which this event has occurred. By combining the two, you can put cosmological constraints just if you can measure the redshifts of these events. And how to measure the redshifts of these events is going to be the next few lectures, basically. Okay? Sorry, wait. This iota is different from this eye. So this is actual, the complex eye. The inclination, yes.
So how it is well defined? Because Earth is moving around, the detector is moving. So
yes.
It's like perihelion or the apiarian,
Yeah, so all of these things have to be taken into account. So that's why the location of the Earth, how it is moving around, what is the direction of towards the CMB, and how our galaxy is moving up. All of these things have to be properly taken into account. Because all this motion will also cause like small changes in the frequencies, right? That you see. It's the peculiar velocity of our own galaxy. Right? No, but I is related to the inclination angle. It's related to our line of sight directly.
Yeah, but I mean, like the Earth astronomical unit, it would change, right?
Oh, yeah. But okay, you can calculate at what distance the parallax becomes negligible. Yeah. So that's the reason why you cannot use geometric parallax distances much beyond the galaxy anyway. They are so far away. Exactly. Yeah. Yeah. So this does not matter much. But the velocities, etc., you would have to worry about. The frequency it's yeah. It is a constant, of course, during the time period, but wherever it is, you may have to take that into account. Okay. Okay. So let's look at GW150914. So this was this first event that was detected, and let's try to see if we can see all the different degeneracies that we talked about, whether we can see them here. So this is M1 in the source frame and M2 in the source frame. So when people show you something like this, you have to understand that they have used a fixed cosmology and turned the distance measurement or the amplitude measurement into a distance measurement into a redshift, and then from the redshift and the chirp mass, which is detected in the detector frame, got the source frame chirp mass, and then calculated these kind of plots. Okay. You see a degeneracy like this. What does this tell you? Why is there a degeneracy like this in M1 and M2? Because they can be exchangeable. Why can they be exchangeable? Because you're measuring the chirp mass, right? And so you look at the definition of the chirp mass. Okay, you can see that if you increase one, you can get the same chirp mass by decreasing the other. Right? Yeah. Yes. So, I mean, so then you need to measure more and more things. I mean, more and more precisely, and then you can get more information and try to break some of these degeneracies. But even this is quite a loud event. Even for this, you can see the degeneracy is pretty much there. And this degeneracy, you should try to plot what is this degeneracy direction. Does the chirp mass, does lying on this line give you an equal chirp mass? You should try to figure that out. Yeah. For this, it is quite much, right? You observe also many cycles there, right? Okay, so you can try to see this M1 and M2 and try to, so based on the derivations that we did, etc., those things actually do pop out in the results as well. Okay. Yeah.
I have seen the stellar graveyard picture. So how do in that plot, how have they broken the region?
Yeah, so I think they basically give, it's not like they don't give you the full posterior, right? They give you the best fit masses, right? And so there is a best fit value for M1, there's a best fit value for M2, or the peak of the posterior distribution. That's what they are giving basically at that point. Okay? So even here, you can get a value for M1, a value for M2. You can put it on that stellar graveyard picture that you have. But in reality, they will be degenerate. There will be a degeneracy.
But how are this problem? It's at least in the equation.
No, so you do the full waveform. If you don't just restrict yourself to Newtonian gravity, you write down the full waveform and you start to see that there will be some differentiation that you can do. So this Q parameter that he was talking about. Exactly. So the more details of the waveform that you can measure, you can exactly. Yeah, so typically, I mean, there are assumptions that are made, but then you again put that as a free parameter, marginalize over everything, and then try to get the best constraints that you can get. And here what you're seeing is the degeneracy between the distance and the inclination angle. And so you do see, again, these kind of degeneracies pop out, okay? The ones that we had talked about. So maybe 5 minutes remaining, so maybe I'll stop. Yeah.
Even if you just take the first correction, difference of mass,
Yeah.
you can break the exact detail.
Yeah.
It will be highly correlated, but
Yeah. So this is not, is this the first? No, this is not the first PN, right? You have to go a little bit beyond, I think. One more beyond. Right.
so what? 1.5, just the one PN itself has a mass. So what is the practice?
Yeah. I don't know if I have the, no, I don't have that equation here, but yes, indeed, there is.
A quick comment.
Yeah. Oh, sorry. Yes, Prayush.
For the event that you're showing, actually, what we see is mostly the very last cycles before merger and merger.
Right.
And there, the inspiral is not dominated by radiation reaction anymore. It's mostly the black holes plunging into each other. So the degeneracy is of total mass.
Oh, this is M1 plus M2, you think, rather
Yes.
than the chirp mass itself?
Exactly.
Okay. Okay.
It's the total scale of the problem.
I see. I see. Okay. So you should check check these things out. Okay. Okay. Then the other thing that you can do is the localization of these gravitational events, and this is the last thing before we stop. And so the gravitational wave events, the way they work is you have an interferometer at one place, there's another interferometer. So if a gravitational wave is traveling, say, from that direction, then it will reach the first interferometer at one time. And then to reach this interferometer, it will take some another time. So if you can measure this time delay between the interferometers, you can again localize where exactly where exactly in the sky this event is happening. Okay. Now, if you just have two interferometers, it gives you a degenerate combination, right? Because let's suppose one interferometer is there, one interferometer is here, and there is a time delay, then there can be a wide circle on which the event is located and still give me exactly the same time delay. Okay? But if you have multiple interferometers, then you can start to break these degeneracies as well. So it works roughly like how our ears work. If someone is talking, then one of my ears hears the voice a little bit earlier compared to the other ear. And so that can help me figure out the direction, even if I close my eyes. And so is basically the same principle. The other thing that happens in gravitational waves, which is similar to what our ears do, is that our ears have folds. And so it's not exactly like a uniform response to all directions. Okay, so because the ears have folds, they have different responses in different directions. So you can again start to break some of this degeneracy that I was talking about just based on the time delays. Okay. And so putting it all together, you can actually localize these events. And so this is showing you the localization. Oh. This is for the binary neutron star merger. I don't know why it's not working. I need to play it on the. Yeah, so if you just take two of the antennas, so this is, I think, the Livingston antenna pattern, and then if you take Hanford and Livingston, then you can localize it along this circle. But then because of the differential antenna patterns, you can actually show that it is only a few of these ellipses on this localization region where it can lie. And then you combine whatever amplitude was seen also in Virgo, and then you can start to pinpoint exactly where that gravitational wave event happened. Okay. So the localization happens because of having these interferometers at different places, and then seeing the gravitational waves, the time delays from these gravitational wave events, and the amplitudes as well. Because the amplitude is not going to change that much because of the distance difference between reaching one detector and the other detector. So the consistency of these amplitudes plus the time delays, you can put together to know where roughly these events are localized. And if these events are localized, if these events are localized, if they are localized well, then you would know exactly the galaxy where this gravitational wave event happened. If you know the galaxy, then you can get the redshift. If you know the redshift, then you can do cosmology. Right? So this redshift will be important, but the reason why it is difficult is because the localization areas these days that you can do with the current generation of detectors is still quite large. So hundreds to thousands of square degrees. And so within hundreds to thousands of square degrees, there are many, many potential galaxies. So given that, how to get the cosmology out, that will be the next few lectures. Okay. Okay, so let's stop here for today. And then we'll continue with the tutorials in half an hour and then go to the next lectures tomorrow. Okay. Thank you.